This presentation is Asynchronous Evented Messaging with AMQP, Kombu, and Gevent. I think one of the longer titles we saw on the billing for the conference. My name is Travis Mehlinger.
I'm Aaron Tygart.
We are both engineers at Firehost. As you can see there, our marketing team loves to put our name all over the stuff we take around to conferences.
Including our chests.
So to the other sponsors, we apologize, they insist. As I said, we're both software engineers at Firehost. We use a lot of the technology we're going to discuss today to work on, we use a lot of the technology we're going to talk about today to power the infrastructure management systems that Aaron and I develop at Firehost. To give you a little idea about our background, we both started at Firehost a couple years ago. We were systems engineers for a little while, kind of working on infrastructure problems, and then because we both had an aptitude for Python and we were interested in solving some of those problems, we became developers to actually work on managing infrastructure. So that's how we got to where we are, and some of the context for the technology we're going to talk about and some of the decisions we made, so on and so forth. So to kind of summarize what we're going to talk about, why we're talking about AMQP and Kombu and these sort of things. The most obvious thing is modern applications need to be reliable, they need to be scalable, they need to perform well, they need to be very, very flexible. We put this bullet in here so we had something painfully obvious to say right up front. Nobody wants to write slow and clunky applications, but these kind of things help us make applications that satisfy all of these needs. In particular, we find with the things we're working on that AMQP in particular helps us solve a lot of these requirements. We'll elaborate a little bit more on what nice things AMQP gives us to solve these problems in later slides. Then beyond AMQP, AMQP is Advanced Message Queuing Protocol. It's an open specification for messaging. I think we'll talk a little bit more about it in detail in just a little bit. It's a good question, thank you. So Kombu is the bridge for us from Python to AMQP. Kombu does a lot of nice things that mean that we don't have to do a lot of low-level work to actually do things that integrate with AMQP. And then obviously the other topic of discussion is Gevent. We like to use Gevent because it gives us a lot of flexibility and a lot of performance for some of our use cases.
All right, so AMQP is a RabbitMQ and Exchange messaging platform. Let me dig out my notes here, sorry. This one's driven by a message broker, which is different from other messaging platforms you might be familiar with. Like people use ZeroMQ as an example, I think, of a messaging platform, but it's brokerless. It's really more of like a high-level sockets library than it is a messaging system like this. You might be able to use Redis to do messaging and stuff like that. Lots of people do. In fact, one of the libraries we use today is good, that has that feature. You could use Redis as a backing component for it. We took a look at Stomp, and that didn't really work out for us. It's kind of it's a plain text system, and I think most of the implementations are written in Java, and we're not Java guys, so we wouldn't be able to work on it as much as we do with what we do today.
So to talk about AMQP in a little more detail, to kind of frame how we use it, what AMQP can actually do to solve our problems. This is this gives you an idea what AMQP message flow looks like. Basically, it is it's a brokered messaging system. The important concepts in AMQP are the exchange, the queue, and then the producer and the consumer. An AMQP producer sends messages to an exchange. An exchange is kind of a logical entity that lives on the message broker, like RabbitMQ or QPID, the services you mentioned. Then when things declare queues, which are messages land, they tell RabbitMQ how they want messages to flow from exchanges to queues. And then from there, those consumers bind on any of the queues they care about. And then when messages come into exchanges and get put on queues, messages get copied to any queue that has a matching key. Any consumer that's on a queue gets messages in a round-robin fashion. So one message lands on a queue, then one consumer will pull that message off the queue. If there are multiple consumers on a queue, then they just kind of get fluttered off to consumers as the messages hit the queue. So kind of give you an idea, AMQP has a number of features for how it can send messages to exchanges, or to queues from exchanges. The one we like to use is a scheme called topic, where when you bind a queue to an exchange, you can give it this key with a number of wildcards in it, so you get some flexibility with how the messages flow around. So you can see here that we have a binding key from this first queue to an exchange where the routing queue is star.y.z. Star would match one token in between dots. Further down, you can see that this queue has two bindings. It matches anything x.y.z or x.hash, which will match 0 or more things. And then if you suppose a message came in with the key x.y.z, that would match a routing key for each of those queues. You see star.y.z on the first one, x.y.z on the second one. That message would get copied. Likewise, if you had a message come in with the routing key x.a, that would only match the second routing binding key on the second queue, and then it would only land on that queue, not both of them. So that gives you some idea how the message flow works.
All right, so you're probably asking yourself now, well, why would I need to use this? I've got lots of great interfaces like REST, HTTP. I mean, you have so many options out there right now as far as protocols go, but one of the really important parts about messaging is that you get to decouple services from each other. That means that when you want to send messages, all you have to worry about is your interface and your data getting to the broker. That's all you need to worry about. You don't have to worry about what IP addresses my remote service have. You don't have to worry about failovers. You don't have to worry about ports. You don't have to worry about protocols. You just send data and an interface across the wire. When you get libraries like Kombu and other stuff like that, they'll even handle things like connection pooling and stuff like that for you. So you don't even have to worry about much of anything at all. You just delegate all that stuff to library code. Write important things, not library code. Brokers like RabbitMQ give us extreme high availability, right? So whereas a guy might have to write he might have to use what's it called? He might use Nginx to load balance between two RESTful services or whatever like that. Instead, you just let RabbitMQ cluster and send your messages out there and let it worry about it.
The important thing to remember about how a messaging system like RabbitMQ works is that when you send a message into it, you get a reasonable certainty that the message, once it's in the broker, is going to get delivered to some consumer that actually cares about that message. So then, once you have that guarantee, as long as a message gets in there, the only thing you have to worry about on the consumer side is that should information get delayed, suppose you have a problem with the broker where it's not sending messages very quickly, or you have a service that goes down and it's not actually producing messages for a few minutes that some consumer would need, and then you restore service and it starts sending messages again. The only thing you have to worry about on the other side is that you actually tolerate or gracefully handle messages being delayed, and you're not concerned about how things are actually communicating, whether they're up, what happens in a fault condition at the transport layer. The only thing you worry about is what to do in the event that information isn't there when you expect it to be. So now that we've talked about why you would use messaging for communication, we can talk about why AMQP in particular for messaging, because there are a number of other options. Like we mentioned earlier, you can use AMQP, like we're talking about here, which works on RabbitMQ or QPID. You could use Amazon's simple queue service. You could use Rackspace's queue service. You could use MSMQ. There's a number of options. But we like AMQP because RabbitMQ is a fantastic piece of software. It is written in Erlang. Erlang is built for extreme availability. If we had more time and we're a little bit smarter than we are, we'd probably give up the life of being Python programmers to go be Erlang programmers because Erlang is so cool. But it is what it is. We'll stay Python guys for a while. RabbitMQ is great because it gives us all the messaging patterns we care about. We can do topic messaging, which solves most of our problems like we discussed a minute ago. You get great performance out of RabbitMQ. A sufficiently built RabbitMQ system can push tens of thousands of messages per second, which is beyond anything we're doing right now in our systems, but grants us a lot of flexibility and scalability going forward in the future. We can just go vertically with some of our brokers to handle more message load, and then we just don't worry about that part of our stack. Then we also get clustering, high availability, and federation. We can cluster brokers together. That way we get availability at the transport layer. Should one broker go away, the other broker will continue handling messages. Our services will reconnect to the new broker, keep on trucking. And then we get federation, so that if we want to run services in isolated locations that need to communicate with one another, well then they connect to a broker with some locality. And then again, we can rely on the broker to actually forward messages around to other locations. And then Again, the only problem we have to worry about is what we do if we're handling delayed information. The other thing it gets us is, and I already elaborated on this a little bit, is that it transparently handles the difficult transport layer problems. Aaron mentioned that you don't worry about protocols, you don't worry about failing over your services, you don't worry about those things because it just connects to the broker and then goes and does its thing. Another great thing about AMQP, RabbitMQ in particular, is it's supported by everything you could possibly imagine that you would ever care about. Even, I think we have some examples on the next slide of things that actually use AMQP, but Celery is a task system that uses AMQP. There are a number of, I won't try to remember off the top of my head, I'll just skip over to the next slide here in a second. Actually, I think it is the next one. Yeah, there we go. So tools and libraries that use AMQP. Celery, obviously. VMware's vCloud product will send you notifications about what's going on in the infrastructure over RabbitMQ, AMQP. Logstash, syslogng, FluentD, these are all logging systems, logging syncs that can then forward messages out over AMQP to AMQP consumers. Elasticsearch will use AMQP as a source. Graphite, if you guys use Graphite at all for storing and viewing statistics, it is poorly documented. If you go look in the Graphite documentation for how to use Graphite with AMQP, there's a bullet that says AMQP and nothing after it. Fortunately, it's reasonably it's self-documented in the configuration, so if you wanted to source statistics into Graphite using AMQP, you can do that. You send messages to an exchange that you configure in Graphite. It has a queue that it binds on the exchange that you tell it, and then you can send tons and tons and tons of metrics into Graphite over AMQP.
Furthermore, it's one of the better ways for setting up like a highly available Graphite cluster, because they'll pull data off the queue simultaneously, so you can have more than one Graphite node, which may not be important for all, but for some it is.
To elaborate a little bit, the way that works is we discussed a minute ago how if you have multiple queues that bind on the same key to an exchange, then the messages will get copied. That's something we rely on with Graphite, is we set up 2 Graphite instances that bind to the same key. They've each got their own queue that they're pulling messages off of, and then whenever we send metrics to that exchange, it gets copied to both sides. So if one of our Graphite instances goes away, we take care of that in the load balancer. We just fail that node, and then we can still go get our statistics. Keeps working just fine. Question? I couldn't completely hear you. That's right. We have a publisher, the broker, and then on the other side we have a subscriber to messages it's interested in.
So is it possible, like in GeoMQ world, like we can create one publisher and n number of subscribers to handle the whole traffic?
Mm-hmm.
So are you saying like it depends upon the requirement, we can go ahead and create multiple brokers to handle the traffic?
That's right. So the question is, if I understood correctly, that what he can do in ZeroMQ is have a number of clients that are interested in a particular class of messages, and then handle them. The question is then, can you have multiple brokers handling all this information and then maintain availability?
Yep.
Yeah, and that's absolutely what you can do. Is if should one of those brokers go away, you can configure, and you can do this very selectively. We won't talk about it in detail, but you can tell it which exchanges, which queues you want mirrored to make sure that the queues and exchanges themselves and the messages are mirrored on both sides, so that should one of those brokers go away, those messages still exist, and when your services reconnect to a new broker, then they're able to subscribe to those messages right away.
But is there a guarantee like each broker will receive equal amount of data, or the data should not be duplicated?
You can control that. So any data you want duplicated both sides, you can tell it to do that. If there's uninteresting data that you don't need duplicated on both sides, say it's you have a performance concern about mirroring those messages across both sides, but they're not actually important, you don't have to mirror those messages. You don't have to. So you can be very selective with how you handle that. Does that answer your question?
Yeah.
Okay. If not, we'll find you afterward and talk a little bit more about it. Okay. So we kind of blew through that pretty quickly. Now we've actually got kind of four different code samples. We'll talk a little bit about using AMQP by itself with Python, then introduce Kombu, and then introduce Gevent, and then introduce Kombu and Gevent, kind of put all these ideas together. So Aaron will discuss our plain AMQP examples. There you go.
So we're going to start out with the canonical examples as given by on RabbitMQ's website. I've actually ported their examples that they have to. They prefer to use Pyka, and I prefer to use the AMQP library as it's more pure to the API. So we're going to follow a couple folks' good advice right off the bat. We're going to start out by setting up our logger so that so we don't use print statements. We're going to because we're connecting locally here, we're going to fire up a connection to the local RabbitMQ instance. Where is it? It's
we have the web interface running here with a local RabbitMQ instance.
Yeah, so there's really nothing important there yet. So then we're going to set up a channel for communication, and then we're going to go and set up a. We're on the. Let me start on the sending client. That makes a little bit more sense. I like the idea of messaging because basically for certain use cases, which I'll come across a couple of them later, you can just start sending messages to the exchange, and as long as nothing is binding to that information, they'll just get sent into a black hole. And then when it comes time to figure out whatever to do with that information, you go write your service then, and not. I mean, so you can just, let's say you had log events or statistical information you just wanted to start spewing out from one of your services, but weren't really sure how to use it yet. You just put those little hooks in your code and just start sending information, and when you find a good time to make use of it or whatever, the information will be there ready for you.
Before we get too deep into this, there are a couple things I want to mention. One, we kind of made a challenge for ourselves last night. We had all our code ready to go, and then James said in one of his James Powell said in one of his presentations yesterday that it would be nice if people only did Python 3 in presentations, so that the rest of the world only sees Python 3 when they're going to look at all these Python conference presentations. So we decided, what the hell? Let's see if we can port this to Python 3 in one night. And it turned out to be a much bigger challenge than we expected because Gevent doesn't actually support Python 3. So someone fortunately out in the world of open source had made a fork, put it on GitHub. It works great with Python 3. So the disclaimer with this code is it is Python 3. It works, at least it did the last time we tested it. And you should not do this out in production for anything because Python 3 and Gevent is absolutely experimental. But it was a fun exercise, and all the code you're going to see up here is Python 3, so you can have that expectation right up front.
All right, so we're this is finally so we're working on the Hello World example, which is the first example on the RabbitMQ docs, right? So we're going to go and set up our connection to the broker. We're going to make a channel of communication on there, and on that channel, we're going to make ourselves the hello queue, and because this is Hello World. We're going to make a message object with the body Hello World, and we're going to publish it to that channel with the routing key hello. A routing key is an additional bit of information that tells the broker what to, not the broker really, but it tells a future consumer where it belongs, right? You're just going to give it, they're usually namespace. This one's really trivial. This will start to make a little bit more sense when I get to the later example where we do like logging. And then, because we're a good app, we go and tell everybody that we just did a thing, and then close a connection. I mean, this is really simple. There's not a whole lot going on here. And on the other side, we're going to go and declare the same queue, and we're going to go and make ourselves a callback that just logs, hey, I received my message, and then we're going to set up the channel to map to that hello queue and call that callback when it receives a message, and then we're just going to keep looping forever as we get information. Where's my? Well, I want
Oh, yeah, sure.
Can you actually move through? Never mind, don't worry about it. So yeah, we saw that message was already actually waiting for us on the broker where we connected our receiver. So that's part of what we're trying to illustrate today, is that your broker ends up being your availability concern. It takes care of all that stuff. And you can watch me here. I'll just go send a whole bunch more messages and just go hog wild. You can see how, I mean, it's real straightforward. And because I'm lazy, I didn't set up a signal handler or a try-catch keyboard interrupt because, well, there's been a lot of boilerplate code when I'm just trying to show a point here.
No, so the routing keys, queues, exchanges are all kind of independent ideas. So a good analogy is you can think of queues, exchanges, routing keys like the mail room in an apartment building. So bags of mail come in. The mailman brings in bags of mail to an apartment building, and then they need to go into mailboxes in the building. So you can think of the building like the exchange. This is where all these messages need to go to get to some consumers, the residents in this building. And then the mailman goes through pieces of mail individually, looks at the address on those pieces of mail. Think of the address like the routing key. The routing key then dictates which queue it should go into. Think of a queue like a mailbox somewhere in the room. So then once he's examined that routing key, identified the right mailbox, queue it's supposed to go into, there it goes into the mailbox and it's sitting there waiting for a consumer. So, mailman is the conduit for something to send messages. The building is the exchange. Addresses are the routing keys, queues the mailboxes. Then, one thing that's important to remember is that, and he just demonstrated this here where he sent a message before he actually brought something up to consume it, is that the resident doesn't necessarily have to be there to actually get the mail at the same time. A resident could be there and pluck the mail right out of the box just as soon as the mailman puts it in there, but it could sit there for a day before somebody actually comes and gets it. So.
Well, that's also not strict messaging semantics there too. The RabbitMQ and AMQP offer like incredible flexibility for what you want the messages to do, durability, whether or not you need to know if it actually got there. I mean, you have lots and lots of options, so that can all be changed. It's not like absolute gospel.
Sure. But in the basic case, that's pretty much how it works for topic-based routing.
Okay, so in this case, this example, we're going to set up a durable queue, and in this case, durable queues and durable messaging means that if the broker goes down, it's saved that information to disk. So you can bring the broker back up, and it'll still have that information there. And this one gets a little bit more. That's what durable true does right there on the queue declaration, and that's what delivery mode 2 does on that message. And this one we're a little bit more flexible with the data we're going to send. It's not necessarily hello world. We're also going to accept whatever we pass, or if we have options on command line, we'll pass those in. And in this one, we're also going to use this since we've named it task queue, we're going to pretend like we have a unit of work that we're going to ship across the wire. So we'll count the number of periods in the message, and we'll wait a little bit to pretend like there was something to do. We have like totally different workflows, you and I. What was that called? So boom, we saw that got done right away. And it's going to take a little bit to process that one. It's done. So I mean, we have a simple queue system here showing off. Not really a whole lot to say there. I'm just trying to demonstrate how easy this is, how quickly you could be into this and experimenting with this in your projects. And then we're going to start using what's called a fan-out queue. Travis, can you tell us a bit more about queue semantics?
Sure. So the most
exchange semantics. Sorry.
The most interesting routing scheme and the most flexible that we talked about earlier is the topic-based routing scheme, where you have some kind of key that can have wildcards in it, and then you can use that to kind of dictate with more flexibility how those messages actually get routed wherever. The other routing modes that AMQP provides are direct, where you provide some kind of you provide a key that is supposed to match exactly some binding between queue and exchange, and then, excuse me, and then, any messages that come in that match that exactly will get dumped on a queue. That's not terribly useful because it doesn't give it a whole lot of functionality.
But, it's worth noting that the previous two examples actually used that method, which is why we're just now getting into exchanges. Sorry.
Sure. So direct isn't terribly useful because you get like a one-to-one relationship between, or not necessarily a one-to-one relationship between your bindings between your queues and exchanges, but you don't get the nice flexibility that you get out of topics. And direct is really just a subset of topic anyway. What he's going to demonstrate here is fan out. So you can declare what's called a fan out exchange, and then any queues that are bound on that exchange then get all of the messages that go to it. So whereas you have to do a little bit more work with topics, to make sure to ensure the messages get copied to a number of different queues that are bound on that exchange, fan out is a little more naive, where you have queues that are bound to a fan out exchange, and any queue bound to that fan out exchange is going to get a message that hits that exchange.
So yeah, we have the same boilerplate as before, except right now we're going to declare the logging or the logs exchange. That's a fan out exchange. We're going to do the same processing that we did before, where we'll just take in whatever messages were passed in on command line, and we're going to publish this message right to that exchange. The receiving end is similarly simple. We declare the same exchange. You need to remember to use the same exchange declaration on both sides. That an unequally defined exchange declaration is a violation of the constraints. So we make a queue on that exchange, and we make it exclusive, and then we bind it to that exchange. We have a simple logging callback here, and we set it up to drain events for forever. To properly illustrate this, I'm going to show, we're going to fire up two receivers this time. And we can see right there, they've been duplicated to both sides, and so on and so forth. It's no more to say about that. And then so, you look at something like this and you're like, okay, well, I want to make this logging a little bit more powerful. In a traditional logging system, I mean, it's not just a log, right? You have a computer system that has different facilities, different log levels, a bunch of different metadata that goes along with it. It's very important for deciding whether or not you actually want to listen to those logs, right? So you don't want to publish a whole bunch of data and have everybody write everything to disk. So we're going to add severity to this situation here. So I've started out by just starting up an argument parser. The RabbitMQ docs like to just use sys.argv, and it's a pain in the neck. And this argument parser is so nice and so easy to use. Just use it. So we're going to start up another direct exchange so that we can show off the severity. And where am I going here? And you can notice that we're going to pass in severity as an option in addition to our message, and we're going to use the severity as our routing key. The receiver will do. We're going to add arguments when we fire up the receiver that will allow us to determine what kind of messages we want to listen to. So it's gonna have severity as an option, and it'll take more than one. So we're gonna go set up the same exchange, fire up a queue in there, and then for all the severities that have been passed in on the command line, we're gonna bind our queue to those severities. So all those individual routing keys that we're going to make with the log emitter, optionally we're gonna bind on with the receiver. Our callback is a little bit different this time. This time we're going to denote what our routing key was when it came in so that we can see what severity it was that got passed in. And then we're going to do the same thing. We're going to drain the queue forever. So. So we're going to go and change the different severity here, and we're going to observe that it's not going to pick it up. Here. And it didn't pick that up. Meanwhile, we can go fire up ourselves another one here, and I think you guys see what we're going to get out of this. And so that one receives good messages, the other one receives bad messages. It's real straightforward. That's the very simple basics of routing keys and what you might, and just starting to like break into what is really powerful about messaging and routing. So for our final example with just the plain AMQP libraries, we're going to go a little bit further, and we're going to get more advanced in our routing, and we're going to go to a topic exchange like Travis and I enjoy so much. Topic exchange allows some more advanced routing. In this case, we're going to use two factors to route a message. We're going to have a facility, so where did this message come from? And we're going to have a severity, and we can decide how severe it is. And the key binding semantics of AMQP allow us to use wildcards. We can bind on everything. We can bind on specific individual routing keys. We have lots and lots of options. So this allows you to configure your remote receiver to receive anything you'd like. So if you want to hear everything from, your DNS server, you can bind on bind.star. If you want to know everything that's like a big alert, you could go on star.error and catch everything from every service that is an error.
Block pattern, or is it as full as regex?
It's a very simplified regular expression. So star would match a single token.
I think it's glob, isn't it?
Oh, I didn't hear you say glob. Yes, it is glob. You're absolutely right.
Yeah, so they have it's not like bash globbing. They have hash, I think, binds on everything. I think there might be a couple different, I don't know. We can pull up the details later.
Yeah, hash will match 0 or more tokens, dot delimited tokens, and then star will match exactly one token.
So once again, stability and severity are just options on there. We set up a topic exchange here. We're going to go and build our routing key out of the facility and the severity. It's dot delimited in this case. And we're going to publish to our topic logs exchange with the routing key that we just built out of the facility and the severity. And also, of course, tell us what we just did on the command line. And the receiving end is also very simple. All of the positional arguments that are passed into this program are going to be the different binding keys that you want to use. So what we're going to allow the RabbitMQ semantic or the AMQP semantics to be passed right on through. So if you want to bind on wildcards, we'll allow that from the command line. Once again, same exchange. We dig ourselves up a queue, and then for all the binding keys that were passed in, we're going to bind on them on that exchange. Simple callback. We're going to print the routing key again so that we can see what's where it came from and how severe it is. And then we're going to go and loop. It's notable that we're going to turn on no acknowledgement here. We figured that a logging system is probably going to spew a whole lot of information, and generally logging systems are done in like UDP and stuff like that. They aren't really concerned about ultimate reliability. They should be pretty reliable, but it's not a big deal if you don't get acts on everything. So we're just going to turn them on and just not waste that exchange time. RabbitMQ has a bunch of really interesting statistics that they ran. They were benchmarking their exchanges or their broker, and you can see what things like acts and durability and stuff like that. They can show you what kind of impact that has.
To elaborate, he mentioned earlier that durability is, should the broker go away, it's periodically saving these things to disk, so when the broker comes back, you don't lose that information. Message acknowledgements are what a message receiver does to indicate to the broker that it actually got the message successfully. And here, in order to kind of demonstrate, like he said, that logging isn't necessarily what we would consider critical information, we won't worry about message acknowledgements. We won't concern the broker with whether or not the messages actually got delivered correctly to the receiver.
Cheerleaders are excited, aren't they? All right, so let's see here. We're going to set up our receive logs, and we're going to just let it bind on everything for now. Forgot how this works. Just even. Oh, there we go. So by default, I think we did the anonymous.info for by default, and then because I'm a child. See here. So we'll go and demonstrate how the wildcards work here. So if I wanted to see all critical errors, and I'll go and fire up another one so you can see that all messages are going through. So you can see that we got it on both sides there, and then let's see here, we'll go and say you can see that obviously our logger that was bound on critical did not need to know that so-and-so logged into the MySQL server. On the same token, you can go and do something like this, right? And anything destined for MySQL, not at any severity, will get logged there. We can go back and find my bind message again. You can observe that it's not going to go to our MySQL logger. It's incredibly straightforward. And so that's the AMQP library. It's a pretty faithful implementation of the AMQP API. We're going to move on into Kombu. Travis, please. I've spoken enough for the moment.
Sure. So Kombu's a library for Python that basically implements producer and consumer. The nice thing about it is, like you see here, that it does producer and consumer pattern for you. So what you saw with the examples that Aaron put together using low-level, if you will, AMQP, he did a lot of work with setting up, connecting with, opening a channel, with declaring exchanges, with declaring queues, setting up bindings, all of those things. Kombu takes a lot of the work out of that, where you're working at the producer and the consumer level. You say, I want a consumer that is, declares these queues and exchanges, and I'm interested in these kind of messages, and then it does a lot of the bookkeeping work for you. It does connection pooling, it has producer pools, it does all of that stuff for you. The other nice thing about AMQP, or the other nice thing about Kombu, is that should you not want to use AMQP, and there are plenty of good reasons not to use AMQP, it's, if you didn't have the performance and availability requirements the AMQP provides, it's kind of a hoss of an application. Kombu hooks into all of these other tools pretty much transparently. It would require minimal changes to your code to take a Kombu-enabled producer or consumer, send it over to use Redis or something like that. So we got a few more code samples to demonstrate how we work with Kombu. Aaron has written these as well, so I'll let him speak a little bit about them.
Yeah. So we're going to take the example that I just gave where we had the facility and severity logging system set up, and we're going to do them in Kombu this time. And so what? There's not a whole lot going on here. That's too different. You can notice that I don't have to worry about setting up a channel, right? I'm just going to go and set up a connection. And because I didn't actually double check the docs on this, but I think that because it supports so many transports, you have to be explicit about connecting to AMQP. I have to double check that one. And you also have to be, so since Kombu is kind of oriented at the task queuing paradigm, metaphor, whatever, you actually have to turn off a lot of the HA features. So you can see me turning off durable. You can see me deleting the queue after we disconnect, and we can see me putting delivery mode into non-durable as well. So I had to put some effort into that to make sure that it was just a simple exchange without too many features. In this case, we're going to see that Kombu provides connection pooling, which is an awesome little feature. So I am going to go and find a producer out of the pool, and I'm going to acquire a lock on him, and we're going to pull him in to this context. So maybe declare makes an exchange unless it already exists. And then we're going to publish a message with that producer on that exchange using the routing key that we're already familiar with. The worker is where things get substantially different, right? It likes to use a worker model, and so you end up with this consumer mix-in to help you handle messages as they come in. So we're going to start here with the same verbose exchange declaration, turn off those features, and then I'm going to make a bunch of queue objects. It likes to use first-class objects for this case. And we're going to turn off acknowledgments, of course, and we're going to bind each of these queues on the binding keys that are given on command line, just as in our previous example. Where are we? Right here. So I mean, it's the same thing. And then we're going to set up a log worker using the consumer mixin that Kombu provides. When it goes and requests the consumers, this is part of the protocol that they've specified. We're going to go make a bunch of, we're going to make a single consumer using all the queues that I've created up here. And then we're going to call the onMessage function on the local object when one of those things comes in. And when those come in, we're just going to print it to the console, and we're going to note where what the routing key was used to get here, and we're just going to listen forever. Ugh. And to kind of show off the flexibility here, I'm going to go and use my old log, my old emitter to send information to it. Watch this not work. Oh, hey, that was not. There we go. So there we go. I have a Kombu one up top, and my old regular AMQP one down below. So you can see that it's a flexible. Well, this is a really trivial example, but it's a very flexible system, and you don't really need to worry about which consumer libraries you're using on each side necessarily. In fact, other languages are also easily supported. Our team has a .NET library they use to connect to our Exchange and work with us as well. So yeah, I mean, it's very straightforward.
Okay, looks like we are running a little bit shorter on time. We talked a long time about playing AMQP, so I will move through this as quickly as practical and hopefully not leave out any important information. So the Gevent library is really interesting to us because it solves some problems we have with doing I/O in our services. So we've implemented a service-oriented architecture to manage a number of the things we do with our infrastructure at Firehose. And Gevent helps us solve a lot of problems because it does evented I/O. It has, it's a concurrency library, provides coroutines, provides nice synchronization primitives, locks, queues, semaphores, events, so on and so forth. Computer science students I'm sure will be intimately familiar with those concepts. And we like it because for the right problems, which we feel like we have, it gives us a lot of flexibility for scaling our applications. This, in addition to all the things that we get out of using AMQP. So to talk a little bit about problems that are suited to Gevent, it is not a magic bullet. It is not a Thor's hammer for solving problems. Gevent is really good at doing lots of concurrent operations when you have lots of I/O involved. So suppose you were doing something like a web crawler, you're doing something like a web server, we need to farm out lots of tasks, but they're doing lots of I/O. Gevent is really, really good for that because it's going to, anything that spends very little time doing CPU-bound tasks but does wait on a lot of I/O, it can schedule internally because any task that you're running in the context of Gevent that isn't blocking on I/O, it can stop executing and bring something else up to execute instead. A concept called green threads, if you're familiar with that. So like I said, web crawlers, web servers are kind of well suited to using Gevent. If you're familiar with Unicorn, which you can use to serve WSGI applications, Unicorn uses Gevent in the background. And then it's also good at solving problems where you need concurrency, but threads or processes may not be optimal. So a good example would be where, suppose you have an application where you need to do some I/O fairly intermittently. So it's not doing a whole lot of, say, network I/O. It's not doing a whole lot of network I/O, but it needs to do something every now and then. But you find you spend a lot of time waiting on I/O while you want to do other work. Well, I want to do other work instead of sitting and do nothing waiting on I/O, so I'll fire up a thread. Well, we're in Python, so threads. You have GIL contention process and other problems like that. So you might say, well, okay, threading isn't going to work well for me. I actually want to do a number of things at the same time while I have another thread running in I/O, and then you run into GIL contention. So then you could say, well, I'll use multiprocessing instead of threading. I'll solve this with multiprocessing. I'll have one process that's doing I/O, and we'll use queues to delegate information back and forth among these processes. And then you run into the where'd my memory go problem. Suppose you're actually in an environment that's constrained for resources. Processes may not be optimal. So in cases like those, Gevent is good at solving those problems. Then, on the other hand, problems that aren't very well suited to Gevent would be absolutely CPU-bound problems, because Gevent is going to work in the context of one process. If you have a greenlet that's doing a purely CPU-bound problem, it is going to block all the other work you're doing, and I will demonstrate that here in just a second. So we'll pull up another code sample here. This time demonstrating Gevent, kind of a worker pattern. A producer-consumer in Gevent where there's one worker doing some fake work that we've created. You can see here that we've got some boilerplate for parsing arguments and some boilerplate for actually printing out some logging. And then here we're going to fire up a few queues. These are a primitive that Gevent provides. We're going to spawn some functions that we've basically made a little factory here that makes some different parts and assemble them into widgets and then ship them off. And then, each of these steps in the manufacturing process is going to, fake some amount of time that it takes to do it. I think we saved 4 times random. So, anywhere between 0 and 4 seconds. Excuse me. So we will start this up here. We'll start that. And, oh, wrong example. Try that again. There we go. Okay, so we have these, these producers and consumers making parts going back and forth. And all of these things are running concurrently. So each of those greenlets will sleep, yield to another one, and then you can see at the end that we made some parts and blocks and shipped them all off. You can contrast this. We can kind of fake a CPU-bound case and show what the results are. The fake work function, which I've called sleep here, we can make it CPU-bound by, instead of sleeping in the Gevent scheduler for a certain amount of time, then we'll go ahead and tell it to actually just busy wait, a thing you would never actually do, to kind of simulate that it's doing a CPU-bound problem and blocking all the other greenlets from running. And you can see the results are quite a bit different. So there's an example of why this would not be, Gevent wouldn't necessarily be good for purely CPU-bound problems. So finally, for the last example, we will we'll put together Kombu and Gevent. So we get the power of our messaging pattern and the nice things we get out of Kombu, hook them up with Gevent, get our coroutines, get evented I/O, and then hopefully yield some impressive figures with how quickly we can bounce messages back and forth. So we have another worker pattern here, or a producer-consumer pattern. We're going to have one side that simulates some kind of unit of work when we send a message to actually do some work. And then the other side will send some messages that indicate, how much time that work should actually take to do. So we'll fire up the server here, and then we will fire up our client. And I don't don't have logging displaying, so that's why this isn't showing right. Flip over here, set this to debugging mode. Likewise, do the same here. You can see what's going to happen. This is blocking forever. We should see some output on the console here. And it appears I may have broken something. Our organizers are telling us we're out of time, so if you'd like to see this a little bit further, come talk to us afterward. I think we may have a minute for questions. All right, I think we're all set.
Don't forget about the t-shirts. Yeah, if you want an extra t-shirt, go get one.
All right, question.
Say I have a producer and 10 different consumers which performs 10 different tasks. So I started sending some data to 10 consumers and something was wrong with one of the consumers. And I wanted to debug that problem. So what will be the best approach?
The question is the question how you would debug it, like when it's running live?
Yep.
It's actually kind of a challenge with Gevent, and that's another one of the drawbacks of working with it, is that hooking it in real time with something like RDB, the remote Python debugger, is difficult because it's Gevent monkey patches the standard library to provide all its non-blocking features, and then that has some implications from other parts of Python. We solve that problem by doing pretty extensive logging on all our services. Down to tiny nitty-gritty little details, so that should something go wrong, then we can follow that back pretty easily. And that includes, that's log messages where we elect to actually dump some information so that we can see what's happening. Logging exceptions. We use, if anybody's familiar with Raven, we use that to Raven's the name of the library. What is the service? Can't recall the name of the service, but it's a Python exception logging service. So we do things like that because actually hooking into it is actually somewhat difficult.
Also, lots of testing.
And lots testing. We unit test everything. That makes it a little easier to catch things up front.
Like if you have only 10 consumers, but take an example like if you have 100 consumers and it's tough to dump into the directory and look for a particular consumer log through Splunk or manually. So apart from this option, do you have some other options to handle this situation in terms of RabbitMQ kind of redundancy?
I'm not sure I completely understand your question, so if you want to come up here, we can talk a little bit more about it.